there are many more good jokes. Just everyone should feel free to use.
Okay, welcome back to the afternoon session. As you can see, Professor Keshav Agarwal will continue with his lectures, and this is his last for the.
Yes. So thank you, and thanks to Olivier for for agreeing to swap the lectures. So it's now the final analysis is to take place. The last one was a little maybe not clear, but the main idea is that if one has to do while differencing, you take the fourth power and then you have reduced cubic into a linear factor, at least in one of the variables, and you're reduced to a lattice counting problem. And in order to do a proper lattice count, what we do is use Davenport's shrinking theorem or shrinking lemma, and then we end up getting this particular thing. And so the way we are going to choose, so now we are ready to apply this lemma, both to major, and minor arcs, essentially bounding all the kinds of errors that appear. Also recall that this particular count, which is the number of zeros that f has inside a box such that x goes up to b, is this integral of s alpha. And then we break this into two. We break this into the major arcs and the minor arcs. I'm sorry. Oh yeah, so this one is for everything. This is for all n. But now we will see that in order to get a good estimate on the minor arc, we need n at least 17. This for everything. Right, so this is what we have so far. All right. Okay, so let's first take care of the minor arc because, well, that's the analysis somehow that we have done. And the minor arc, so if you remember when we were, how we had chosen the minor arcs, we had chosen like the major arcs were given by A over Q. So they were around the small q. So q is less than some b to the delta, right? And then this is A over Q minus 1 over, so this goes up to QB cubed was, or was it QB to 3 half, sorry. Of course. Thank you. Yeah. Yeah. So then we had chosen our major arcs and minor arcs, so that for major arcs we get that q goes up to b to the delta, and how big do we choose these theta? That is going up to b to the minus 3 plus delta. Oh, something like so q be cubed. Like this. Thank you. Yep. Thank you. And yeah, let me be sure I don't make any further typos, just so that we are fine. Is choosing the major arcs properly. So instead of so because we had also chosen the theta that way, right? So this was b to the 3 plus delta and plus, this was basically the choice that we had made at the end of the first lecture. So over here, this is this, and the minor arc is the rest of it. So the major arc is delta is the union over all of these q's going up to b to the delta over all the a's m aq, and then the rest of it is the minor arc. So the first thing that we'll do is estimate the contribution of the minor arc just by applying this estimate on the wild difference on S alpha. And so we have this M delta, right? So this particular thing in absolute value, we want to bound this, and over here it can appear basically in two ways. So either Q is somehow too big. So let me write it as two different sums. This is, well, so Q's are going to be bigger than B to the delta. Yeah, we are actually taking delta to be less than half for things to work out. Because in the very first time, what we also had is S of A by Q plus theta is equal to a certain main term plus big O of B to the n minus 1 plus 2 delta. Right? So that's what we had for the major arc thing at the end of the very first lecture. That's how we chose the major and minor. So in fact, we do have delta to be strictly less than half at the end, we'll end up choosing. So that's something. The minor arcs appear if Q is bigger than B to the delta. Of course, the maximum it can go up to is B to the 3/2, right? And then you take all the A contributions. So all of these A modulo Qs where we are fine using this notation with the cross means that they are coprimes. And then the bound on this thing. So this is the bound. So we want the thetas to go from Q B to the 3/2 to Q 1 over S of A. So alpha is A over Q plus theta. So this is basically Diophantine approximation, and you can write that. So when Q is going up to B to the 3/2, you can use this Diophantine approximation to write that. Plus, of course, the contribution so the major arc happens when Q is less than B to the delta and when you're around that. Right? So you have to take, on the other hand, the contributions where Q can be anything, and you sum over all of these A's modulo Q, and how big can theta be? Basically, you have the bound, so A over Q, say, plus minus theta, d theta, so maybe I should have a plus minus sign as well over here. And there, I should write the bound on theta. So how far are we from theta? It can be from B to the minus 3 plus delta to 1 over Q B to the 3/2. So these are the basically two instances where one ends up getting the minor arc. So either Q is big or you are over here like this. Right? So these are the two instances. So maybe I can show you estimates on one of them, and the estimates on second one will similarly follow. Okay, so we need to basically apply our this e to the minus 3, I'm sorry, should be, I'm sorry, let me just be sure again. It should be, I mean, maybe I messed something up over here. So the way, maybe I should have written it properly again. Okay, maybe I'll just take a pause over here just so that I'll recall how the major arc was chosen. So it should be 3 minus delta, right? In the definition. Yeah. So it should be, that's okay. Should be 3 minus. Yeah, I think it should be 3 minus so the arcs were chosen so that we ended up having, so what we had, okay, so I guess aside, what we had is Q times,
Here we see there is no oscillation.
Yes.
So you need to add something.
Something more. Yeah. Minus delta. Thank you. Yeah. So we wanted all of both of this less than b to the delta, this less than b to the delta. Thank you. Yeah. Okay. I hope I'll not make further errors. So we have these things, right? And so at this point, yeah, this is all right. And these are the integrals like this. Okay, and at this point, we apply the while differencing over here. And so we ask what happens if theta is an absolute value less than 1 over q b to 3/2. So we notice which one is the bigger one over here. So it basically matches up, this is the one that should contribute because theta small means this 1 over is big. And so if one applies while differencing lemma at this point, one ends up getting a bound that looks like this. So this is going to be less than how much? So we have b to the n coming from so b to the n log b to the n by 4, that term is obviously there. And then we need a further contribution coming from the minimum of these things. We also have how many q's are there. So q's go from b to the delta to b to the 3/2. We have then all of these a's and this contribution. Okay, so second, this sum. No, this is minor x. Q up to b to the delta is the Are we okay? Yeah. It's fine. Yeah. Okay. Yeah. Okay. Let's see what this is. Let me write all of this a mod q as well. And right, we have this integral. Let me just put it over here. So negative 1 over q b to the 3/2, 1 over q b to the 3/2, and then we put the bound. So at this point, it should be the minimum of 1 over q and 1 over q theta b cube right here. Right. And then it is kind of obvious that this is the thing, which is the min from this. And so I guess if you sum things up, the q should cancel out. And then in this, the integral, what one should end up getting is the bound n by 8. Yeah, thanks. And okay, I should maybe look at my notes instead of the book itself. I had written it properly. Yep. Yeah, so if one does this, this is going to be less than what? B to the n log b to the n by 4. And then we have a q sum between something and something, right? And okay, so there is a q contribution coming from a mod q sum. There is, if I invert it, it's a q common, if you will. So there's a 1 minus n by 8 contribution coming from taking a q out from everywhere like this. And then one has to integrate out this thing. So one has to integrate out this max 1 and q theta b cube b theta. So this is what this is. It's like painfully writing each and every step. But at this point, we'll have to ask. Q's not there. Okay. So at this point, we ask, what is this kind of a contribution? So either theta, so this is going to be max if theta is less than 1 over b cube, and otherwise it's that. And so one can observe that this is actually going to be big O of 1. This part is going to be 1 plus small o of 1. That one ends up getting, just putting this integral. And so the bound that one ends up getting is b to the n log to the n fourth. And then the bound on q. So this is q going from b to the delta to b to the 3/2, q to the 1 minus n by 8. And so at this point, what will help is to take n to be big enough. Right? So this is, remember that this is like, maybe write it like n by 8 minus n. And so the biggest contribution is going to come when q is small as b to the delta. And so this bound is therefore going to be, right, this bound is going to be less than. So if you subtract a 3 and add a 3, this will be minus delta n by 8 minus 2 powers of log. Let me just make sure this is okay. Or let me see if I made an error here. Second. Yeah. N minus 3 by. I'm sorry about tripping up over here. Well. Let me just try to think. So if one does maybe a change of variables, if that helps. So if one does a change of variables, theta going to theta over b cube right over here, then maybe it can kind of help. So if one does a change of variable over here, one gets a theta over b cube right here and a b cube over right here. So that this particular thing is gone like this. There is a minus 3 over here. And then the integral bound is going to be b to the 3/2 by q. B to the 3/2 by q. Okay, maybe this is going to be a little better in these calculations. Now let's try to see what happens right over here. If theta is less than 1, so at this point, you see q is going up to only b to the 3/2. If theta is less than 1, then this is the max, so that this integral is 1 plus something. If theta is bigger than 1, then you get something which is less than 1. So you get the power of 1 over theta to the n by 8. And then you are going from 1 up to b to the 3/2 over q. Okay? And so now that is going to be small of 1. Maybe this is a little better calculation here. So sorry about messing this thing up over here. So that's why one gets n minus 3 right over here itself. And then one gets this particular thing. Yes, at least over here, we are assuming n is bigger than 8. Do we need n bigger than 9 for things? No, n bigger than 8 is good. Yeah, greater than or equal to 8 is good. And at this point, what we basically want is that the minor arc contribution is less than the expected major arc, which is b to the n minus 3. And so this is the point where if one wants that n by 8 minus 2 is going to be something big. So any positive contribution ends up giving us a saving. So this basically means that n is bigger than or equal to 16 plus epsilon. And we end up getting a smaller minor arc contribution than the major arc contribution. So this is what this is. So that's the minor arc. Davenport was able to remove this epsilon essentially, and was therefore able to get n bigger than or equal to 16 variables. Right? So because n is an integer, it just means that n has to be bigger than or equal to 17. And this is the minor arc analysis. Okay. Yeah. So I'll just maybe pause here because I did mess up the calculations in case there is any other questions you might have. Yeah. Okay. So in that case, let's go to the major arc contribution. And the major arc contribution is going to be a union of all of these things. And we had already written the major arc contribution. So what we had said is that if A is less than Q is less than B itself. So for Q going up to D, we had given this expression A over Q plus theta. And this is the first thing that somehow I wrote in the morning that we are going to now contend with. And I just want to make sure that at this point, I'm also not messing up the notations with M's and N's. So I'm going to just stick with the notation of Browning at this point. So this is what we had done after a change of variables, b to the n over q to the n. Then there's an integral. This integral, once again, came from replacing a summation by an integral. And then we had this particular sum of E. And then when we replaced a summation by an integral, this is the error term that we had obtained, which looked like q b to the n minus 1, 1 plus, right? And then we had made sure that both q and 1 plus theta b cube is less than delta for the major arcs. And so this particular is going to be big O of b n minus 1 plus 2 delta. Okay. Since we choose delta to be less than 1, this particular expression is applicable at this point, and we can do the major arc analysis. So for doing the major arc analysis, we want to sum over all the q's that go up to beta, b to the delta. We want to sum over all of these a modulo q's. And for thetas, we want to be around a over q, going up to 1 over b to the 3 minus delta. That's the length. So if you ask what is the measure of the major arc, what's the length of the major arcs? So the total this, if one does, is going to be how much? So you're going to take all of the a's and all of the q's. So you get b to the 2 delta from there. And then you have the size 1 over b to the 3 minus delta from the theta integral. So if you put all of this together, the size of the major arcs is b to the minus 3 plus delta. That's the measure of the major arcs. So if you count whatever that is, second please, 3 delta. 3 delta, yeah. So if you put that together, the error term that you end up obtaining, so error term from in the major arc is how much? So this is big O of b to the n minus 1 plus 2 delta minus 3 plus 3 delta. That's what this is, right? So this is n minus 4 plus 5 delta. And so that also kind of tells us how big delta can be, because you want to beat n minus 3. So over here, this is n minus 3 plus 1 plus 5. Yeah. So delta has to be at most 1 over 5, for example. So you can't go beyond that. So we'll choose delta to be like even smaller. And over here, the expression of I is this. So I of z is given by this integral over a cube of side length 2. So E z. So this is our major arc, right? So at this point, what we want to do is basically show that there is a non-trivial contribution right here, that the major arc does not vanish. Okay? And over here, we'll be assuming a few things about the singular integral and singular series. So for singular series, I will assume that if you have at least 10 variables, you always can find a periodic solution. And for singular integral, maybe say a few more words about how you can actually show that the singular series is non-vanishing. Okay. So I'll just, right, okay, good. So let's do this treatment. Okay, so we would want some contributions, maybe some bounds on IZ as well, coming from, I want to do this first. Do I want to write the major arc contribution first? Okay, maybe I'll first write the major arc. So somehow too many things in my mind, and the last part is a little, I'm not able to plan it properly. So let's look at the major arc contribution, S alpha. Right? So this particular thing is what? So you want Q to go up to B to the delta. Right? So you would want Q going up to B to the delta. You would, of course, want all of these A's, modulo Q. Right? You would want the thetas to go up to 1 over B to the minus 3 plus delta. So at this point, this is an integral of S A over Q plus theta, d theta, and just the main term we have kind of already looked at the error term, 1 u to the e to the minus 3 plus. So this is what we have. And over here, what we just said is that if you expand it out like this, we do end up getting a nice error term. So this is the part somehow that one has to do and put it inside over there and look at what is the integral contributions. So we have to look at what? So the Q sum, the A modulo Q sum, this integrals, and then we have the rest of these things. So it basically splits into two different parts. There is an I theta B cubed, which is coming inside this d theta integrals. And then there is the summation over Q's and the summation over A modulo Q's, which is completely now independent. So we see that if you write it all together, this particular thing is going to be B to the N over Q to the N. We have a Q sum. We have an A modulo Q sum. I'm sorry. That should be very much inside the Q sum. Thank you. Yeah, that should be inside the Q sum. Then we have the A modulo Q sum. And then we have, what else? We have the B mod Q sum. Right, so the B mod Q sum is EA FB over Q. So these are the things that would only depend upon your A's and B's and Q's. And then you have, so this is independent of theta. We have an integral like this, minus 1 over B to the 3 minus delta to 1 over B to the 3 minus delta, because that is, oops, I made a mistake there again. No, we're fine. So that's the length of the major arc, right? So it is around this over here. And then you have I theta B cubed. D theta. Yeah. So this is all of what it is. This corresponds to the main term. Yeah. Plus the error term that we have already written, n minus O plus 5 delta. So this is the error of the major arc. That is the error of the minor arc. And now all of this is the main term. We could also change the variables. Theta goes to theta over b cubed. So if theta goes to theta over b cubed, this goes away. And then this is going to be from negative b to the delta to b to the delta. And then we have to also divide by a b cubed, so you get this. Okay. Good. So now we are in business again. So what we have is b to the n minus 3. We have this particular summations, and we have these integrals. Okay. And so basically the idea is, if we can show that this is something which is positive, we can show that this is something which is positive, then we do get a legitimate main term. And that shows that for at least n bigger than or equal to 17, you do have a count. Okay, good. All right, so then this is what is basically going to give us the singular series and the singular integral. I will mostly concentrate on showing how the singular integral is going to be positive, and we are going to not quite look at it. So the first thing that we do is we try to notice that instead of having this integral from negative b to the delta to b to the delta, you can have it for everything on the whole real line. And similarly, you can extend q not only to b to the delta, but to all of the numbers q. And so if one extends that, then of course one has some kind of an error term that also has to be bound. And the while differencing lemma is again going to help us over there. Okay. All right, so let's try to extend. So I don't want to remove the while differencing because this is something that I will use again. Major arc I have to use. At this point, we are convinced that the minor arc gives us savings. So I'll just remove the minor arc. Of course, the comment I have not made is how big can one choose delta in doing all this. At least from there, we know that delta can be at most 1/5. But one can also try to see what's a good delta at the end of the day. If you put everything together. So let's look at the contributions if you extend the series and sums everywhere. All right, good. Good. Okay, so basically in order to get to how big this contribution is, so the first thing that we want is we'll extend this integral from negative b to the delta to b to the delta to everything. And introduce the error. Which is right, big O of b to the delta to r. This thing. And so if one can bound I theta in absolute value, and then compute that integral, we can see that you have something which is small enough. And so let me, of course, yeah, yeah. So b to the delta to infinity, that is going to somehow give us something good enough. So we want to bound this I theta over here. And let me first, in order to bound I theta, let me first tell you what the bound is, and then we can quickly see that that's the case. I theta is actually less than the minimum of 1 and theta to the minus n by 8 plus epsilon. And this is true for every theta in R. So for every theta in R, this is true. And so this is the bound that one has. Let's try to see if that is sufficient somehow. If you plug in this bound right over here, then notice that theta is going to be bigger than b to the delta over here, so that the minimum is this term. And if you would then look at the error right here, this is less than b to the delta to infinity, and then this is absolute theta to the minus n by 8 plus epsilon d theta. And what is this bound? This is less than so b to the delta 1 minus n by 8. Yeah. And so this is also going to be something which is acceptable because n again is bigger than or equal to 17. Well, okay, this is something that will go on into later on, but the point is you have to look at b to the n minus 3, and then the contribution is this plus delta 1 minus n by 8. This is, yes, that is true. We have to also bound S A over Q, but that is going to be something which is big O of 1. So that's not going to affect. So this is okay modulo the fact that this is small. One over Q to the N is there, yeah. Yeah. So this basically this series is going to be small. So that's not going to affect. So that's one thing. So yeah, how do you show such a thing? Well, maybe I can show this and then take a short break. So let me quickly just prove this bound. Right. So let's prove this bound, and whilst differencing will give us this. Obviously, I theta is less than 1, so that's okay. Because literally just put absolute values inside, you're done. On the other hand, what happens if one takes A is equal to 0 and Q is equal to 1 right here? Okay. So you get S of alpha is S of theta, and then we want to bound S of theta right here. What you end up getting is that S of alpha is, if you take A is equal to 0, Q is equal to 1 while differencing, what we get is that S of alpha, which is b to the n I alpha b cubed plus big O of b to the n minus 1 plus alpha b cubed. So this is the error term that we anyway had. And this is the contribution if you take all of this, just A is equal to 0 and Q is equal to 1. This is going to be, now this is the while differencing part, should end up getting less than p to the n plus epsilon alpha times b to the b cubed to the minus n by 8. Right. So this is what one should see if you put these things. Right. And yeah, feel free to please correct me. I may have unfortunately made some errors in the calculation while writing things down, but I think this should be okay. Yeah, right. And so from this, one basically can get a bound on this thing, right? So if you, for example, take alpha b cubed to be theta right here, just do a change of variables, then one ends up getting from here that I of theta is less than theta to the minus n by 8, b to the epsilon, and theta over b plus absolute theta over b. Yeah, should be true for a priori. It should be true for theta only going up to a certain size. Okay. But the point is, one has to notice is that over here, this particular bound is independent. So theta and b are over here working independently. And so what one can do is extend this to all of the real numbers. That doesn't make sense. So if you choose b as, I guess one has to choose some things a little more carefully. I have to be careful in doing this. So let's choose b to be theta, because over here what you can do is choose b to be what, theta to the n by 8. B is a free variable at this point. That's right. So B is a free variable at this point. But theta is somehow bound, like it depends upon B. We want it to be to go to everything somehow, right? So yeah, 1 plus n by 8. Yeah. If you take theta to be b to be theta to the 1 plus n by 8 now, because b is a free variable, we do that. And then what we end up getting is that this is theta to the minus n by 8 and theta to the minus n by 8. So at this point, then we end up getting I theta less than theta to the minus n by 8. So that's the other thing. So we get theta less than 1 and theta less than, I theta less than 1 and I theta less than theta to the minus n by 8. So that's what we get. So if you extend this integral from b to the delta to all of the real line, then the error that you introduce is going to be acceptable, modulo the fact that if you take this particular sum, then this is also going to give you something which is bounded. Okay. This particular sum in absolute value is, yeah, a non-trivial estimate. Right. Right. Okay. So some saving and we are fine. And then this error term is going to be acceptable. Okay. All right. So I guess at this point, let's take a short break and come back to the rest of it.
You can always do by while you keep
Yeah, yeah. That's basically the point over here.
equal two has to have some size, which it
Yeah,
will have.
it will have. Yeah. So if little q is small, so I guess I will maybe write how one can extend. One can get. This part is always something that kind of trips me up every time. I'm putting this together. Yeah, essentially what one ends up getting again by Weil's lemma. This B mod Q sum is going to be small.
Yes.
So that when, yeah, A mod Q you cannot do much. B mod Q you end up getting by Weil's lemma, which is something small. And then you get that the series is convergent. Yeah. Actually, I'm not. Shall we resume? Or? Yeah, okay. All right. So thanks, Olivier. So I should make this comment. One has to, of course, non-trivially bound this part as well, right? So in order to get that things do converge. So if one looks at alpha in the wild estimate, if one takes alpha to be A over Q, just the rational number A over Q, then one ends up taking theta is equal to 0. And then one asks, what is the size? So if you take alpha to be A over Q, then the size, and you take B is equal to Q, then the size that turns out is Q to the N divided by Q to the N over 8. So that the size that one has is Q to the 7N over 8. And then, therefore, what one sees is that if you look at this particular sum, this is bounded by Q to the 7N over 8. Then you have Q many more things over here, and you divide by a Q to the N. And then you ask, how big is that thing? Right? So all of this, maybe let me just put it over here, and then I'm going to move on to the singular series and integral. So all of this bound is going to be something like this. This is Q to the 1 plus 7N by 8 minus N. So this is Q to the 1 minus N by 8. And then one has to ask, is this convergent? So for example, if N is big enough, this series just converges. So that the error term that one gets out of bounding this I theta by extending it is acceptable. Okay. So that's one of the points. Second thing is that one can also extend all of this to a whole series. So instead of going from 1 to b to the delta, we extended 1 to infinity. Okay. In doing so, of course, you introduce an error, which is going like Q is bigger than b to the delta, and then all of this estimate. So the same estimate applies. So if one extends this, so if you look at the bound like this, so Q to the 1 minus N by 8, again, one wants that you get something which is small enough so that even if you multiply by the error of I theta, which is delta times 1 minus N by 8, then the final error is, or the final exponent is negative, because you want, yeah, and because N is bigger than or equal to 17, you'll be fine. So over here, this is also going to be somehow acceptable because N is bigger than or equal to 17. So this is also somewhere where we are using that N is at least 17 variables. Okay, so this is how one can then get to the final main term. And then the final main term, therefore, at this point, looks like b to the n minus 3, q, which is this infinite sum, and this, which is an infinite integral. So let me write it over there. And now also use the standard notation. So SQF as there is, and at this point, don't think I need the while lemma again. So we can raise this. So yes, at this point, what we can do is that the NFB is equal to certain main term. That certain main term is going to be b to the n minus 3. That's the expected size. And then what you have is sum over all of the q's. So q's, and then you have 1 over q to the n. And I'm now going to write the standard notation. So the rest of it is your SQF. And then you have this integral. So again, let me use the standard notation. So this is this singular integral, right? So what one ends up getting over here plus an acceptable error term. For the acceptable error term, let me just write b to the n minus 3 minus a certain small delta that can be worked out. Okay? So one can choose the big delta properly, and one has this. At this point, if one can show that this is positive and this is positive, then we are done. We do get a legitimate main term. Right? And that is the result that we are after. I will concentrate more on the singular integral because, again, with given the time and I think that's going to be somehow much more doable. Let me first, therefore, look at this particular thing. So singular integral is going to be this integral over the real line of I theta, which is -1 to 1, and E theta fx. So dx, and then we have d theta. So this is what we have. And okay, let me first write what the point is. This particular thing is actually a local density. So what one can show is that this particular integral is some limit as delta goes to 0 of 1 over 2 delta, the volume of what all of these x inside -1 to 1 n such that fx is going to be less than delta. And over here, when I write this, I mean all of the real so vectors or real numbers, x1, x2, xn, right? Not just this. So this is, we can show that this is a local density like this. And if one can show that this particular thing is positive, then we have shown that this integral is positive. So that's what this is. Okay, so now in order to show that this is something positive, what one can do again is use non-singularity of f. So the idea basically is that if f of some psi is equal to 0, then f of psi plus u can't be too big. So that's basically what it is. So if you take fx to be less than delta, and basically and vice versa. So if you take u to be small enough, then you'll have enough number of you'll have a set which has positive density, and it has to have density which is going to be bigger than some constant times delta. That's what one can show. So basically what one can show is that this volume is going to be bigger than delta. Some constant that depends upon f times delta. The way one would do that essentially is inverse function theorem. So you first say that let's find a psi because you can solve it, it's a cubic, a non-trivial psi. And then what you do is you make a small circle around it. And because it's non-singular, therefore del f over del x1, let's say at that psi is non-zero. So you can, because not everything is 0, you can take maybe the first partial with respect to the first coordinate to be non-zero. And then you do a Taylor expansion. So that what you end up getting is that the bound around that point is going to be, the volume is going to be bigger than delta. So that's basically inwards what one ends up getting over here. So maybe what I can try to show is how one gets from here to here. So this is like maybe a standard analytic technique where you take another kind of expression of when a function is supported in a small interval. And so what we can use is this identity at this point. Yeah. So we use this, that integral of sine of 2 pi theta delta divided by theta, e theta y d theta. So this thing is equal to 1 if your y is small, and this is 0 if y is big. Yes. Okay. So that's an identity one can use. Essentially, you have a cutoff for asking when is it that your thing is inside a box of size delta. And so what one can do in all of this is you can expand. Do I want to do this like this? So I guess that's the error that I made, mixing notations from 2 different books, and things got jumbled up. So I have to be very careful in, you know. Yeah. Yeah. You basically then invert that, right? So this is y is your f of x. That's the kind of thing that is happening really. So that, yep. So yeah, so this is a y theta integral that one has. And yeah, so then we introduce this plus an error term. So we will have this particular thing, this integral that we are after, sigma PDF, where you are between negative delta to delta and where you are above it. And then one has to basically bound this and introduce this over here. That's essentially what's happening right here. Okay. All right. Again, I'm just going to say that this bound is going to give acceptable error term because of the lemma that I just removed, because we did get a bound. We did get a bound on I theta from there, divided by 2 delta. Where? Oh, over here. In that expression. No, right now I'm just looking over here. So all I'm doing right now is, yeah, just put it into 2 pieces. That's all we are doing over here. And so at this point, you put it over here, and then you interchange these integrals. Right? So if you were to do that, and you look at this part squarely, then one ends up, and interchange the integrals, one ends up getting basically negative 1 to 1, and then an integral of this sine divided by what that is, and then you have e theta fx, and I should put d theta dx. So this is the theta integral, this is the dx integral, right over here. And yeah, at this point, one uses this identity right here. Now, something is off again. This is going to be the volume of x such that x is less than delta. Okay. Let me just make sure. try to do this more properly. So we do have the identity that I've written properly. And where should that come from? So I should divide and multiply by 1/2 delta. And I'm just seeing if, oh well. In the which integral, this one, this itself, this should be fine, because otherwise you have killed everything. There is really no role of delta over here. So yeah. Here we have one more integral. So what over here, what I'm saying is you can break this integral into two parts, right? And then ask what is this size equal to.
Bounded and lower bound.
Yeah.
Therefore, putting it or moving it next to it can always do.
Yeah.
But just put that there.
So that you can use that integral. And then the point being that this particular integral gives us a 1 if this y, which is fx right over here, is going to be of size at most delta. And then if you integrate over all of x's that are in -1 to 1 in this small box, what you end up getting is, so that's why I'm missing a 2 delta, 1/2 delta somewhere. So this is going to be all of these x's in -1 to 1. Such that this is true. Where should the integral minus delta to delta is already there, but the point is you can also no, this is fine. That's fine. I'm sorry for messing this up. There has to be a 1/2 delta appearing somewhere. I don't think it's going to be very prudent if I say more things about this, but the point over here is that this sigma infinity f is going to be a local density at Archimedean place. And it's going to be something which is non-trivial. It's going to be, it's going to have a volume or a measure, at least delta, given that f is non-singular. Okay, so because f is cubic, you can solve it over reals. And then because f is non-singular, what you can do is do an inverse function theorem argument. And yeah.
In the range minus delta to plus delta,
Yeah.
is bigger than constant times delta and less than constant times.
Right.
And therefore, by inserting it, you are losing 1 delta, and therefore there will be 1 over delta.
Okay. Thank you. That makes so much more sense. So I should just say something like constant times constant over delta, something like this. Thank you. Okay. So that's that part. And basically arguing that this particular density is bigger than delta shows us that as delta goes to 0, that's something positive. So we end up getting that this particular thing is positive. Maybe just a quick comment about why this SQF, this particular singular series, is also positive. The first thing is that SQF is multiplicative. Okay. Again, really not showing you the proofs, just giving comments about these things. All right. So for the singular series, the first thing is that this SQF is multiplicative. So that is to say that SQ1, SQ2 is SQ1, Q2F if Q1, Q2 are coprime. Okay. So that also requires a bit of work. But of course, for multiplicativity, one has to just do the calculation at the prime powers. And then one has to essentially look at this summation and apply Chinese remainder theorem. So if one applies Chinese remainder theorem, you can first break down this Q as a product of powers of primes. And by applying Chinese remainder theorem, you end up getting this as a product of such summations. Okay. So let me just say, how do you do that? This is CRT. Okay. Second. Yes, this is where you need F to be a homogeneous. It's a form, right? So that's one thing. And then I guess one more comment about the singular series itself. I don't want to say a lot because I'm pretty sure that I'll say something wrong, which is not ideal at all. So the other thing that one can show is this. May show that. So once one has this multiplicativity, one asks what is SPF, for example. These are also certain local densities. Okay. So this SPF or sigma PF, how it's written, its limit as k goes to infinity, p to the minus k times n minus 1 times a certain count. So it's the number of b's mod p to the k, such that f of b is congruent to 0 mod p to the k. So we have this thing right here. And so what one therefore ends up having is asking, can we show that this particular thing, this limit is positive? And one basically shows this limit to be positive by using two things. First, if you take the number of variables to be at least 10, then you can always find a p-adic solution. So that is one component. And second, since we have assumed non-singularity, we can, the argument is much easier somehow to show that this is solvable using Hensel's lemma. And it is going to be bigger than some p to the k n minus 1 plus a delta. Right? So that's how one does that. So this is the local density argument that one has. Right? And so that also ends up showing us that this thing is all positive and that, yeah. Okay, and so I guess one last thing, in order to boil down to this thing, what we have is that the singular series, okay, must show this, saves this, and this also needs a bit of an argument. This particular series, which is that. So because it's an infinite sum, right? So things become a little worse for infinite sum. So let me just say one of these things, that this particular series, 1 over q to the n, q bigger than equal to 1, SQF is going to be bigger than equal to 1/2, p less than equal to some particular prime, depending on f, sigma pf. Okay, so maybe this is all I should be saying in this regard. So what one can do is essentially show that this particular singular series, one can show that this is going to be bigger than a finite product of local densities. And then one shows that each of these local densities is positive. I mean, this is true for every prime p. But then the bound that you get here may be getting small as a function of p. So what one wants is, therefore, instead of having an infinite product, if one has a finite product, you are only getting a product with finitely many negative powers of p, and then you're done. right? So that's basically what. So let me just end it over here instead of saying something worse. So we end up getting some non-trivial error term, and we end up getting positive singular series and positive singular integral with the main term of size b to the n minus 3. Thank you. Yes. So Davenport, when he's doing, he does this, that if you have non-singularity, then you can show this b to the n minus 3 like a main term. But if you have a non-trivial singular locus, he assumes, okay, what if, so he does it by contradiction, right? So he says, let's also assume that nf is 0. And if you assume that, then he shows a main term of b to the n minus 3. And that's a contradiction. So that in either case, you end up having certain integer value, integer solution. That's right. Yes, yes. It just says that for n at least 16. Okay, Davenport does at least 16. You have, yeah, 14. Heath Brown does it, right? So you don't have asymptotic. That's very true. It's only for non-singular that you do get an asymptotic. For 9 as well. I mean, Hooley does it, right? So if, yeah, so if you don't have any local obstructions, Hooley shows for 9 variables. You have an asymptotic. Okay, yeah.
Any more question?
Yeah. Yeah, Suraj, yes. Many places, right? Even over here we did, and previously as well. I mean, so in this particular proof, even for proving the Weil differencing, the way we prove it, we did use. Although you can still get the Weil differencing lemma in case you don't have, you have a non-trivial singular locus. Say what?
The variety.
The dimension of the variety. Yeah. Yeah, there we use that. Yeah. Hensel's lemma is easier for non-singular. That's true. Yeah. Yeah. So basically, again, you're inverting. So even for Archimedean local density, given that it is non-singular, it is easy to prove. Yeah. So I guess, yeah, in the main term, we are, because if you do have a non-trivial singular locus, you don't get like an asymptotic, right? You just show that there is some solution.
After the variance problem, blah, blah, I mean, the circle method turned out to be very important, and this cubic form turned out to be one of the very important application of that. And let's thank the lecturer for having taken time to come here and give some 3 lectures on